We have a wheel of radius R, 3,000 kilogram wheel. We have 1,000 Newton force acting radially, acting perpendicular to the radial line, acting tangent to the wheel. And we're going to assume that the force remains tangent to the wheel as the wheel turns, so the force is going to follow the wheel around. Excuse me. We're going to assume that all the mass in this wheel is on the rim, so that the wheel is essentially a hoop. It follows then that since all the mass is accelerating at the same rate and the force is exerted at the position of the mass, that the acceleration, not the angular acceleration, but the acceleration is the force divided by the mass, or 1/3 meter per second squared. That's the acceleration of a point around the arc of the wheel. Now, after time delta t, again assuming the force remains perpendicular to the wheel, okay, perpendicular, and that's probably not a good way to put that, perpendicular to the radial of the wheel, or let's say tangent to the wheel. What's the speed of the rim and how far has the rim moved? Okay. Well, after time delta t, accelerating at 1/3 meter per second squared, the velocity is going to be 1/3 meter per second squared times delta t. So that the displacement is going to be the integral from 0 to delta t of the velocity function, which is of course then equal to the average velocity times delta t, because that by the definition of average value of an integrated quantity, that's the way it is. That just goes back to calculus, one of the most basic results. Okay, the average value of v, since v is a linear function of time, is going to be the average of the initial and final value. Okay, so there's the average. And then that is going to be multiplied by delta t, and it's going to give us, and I don't have my square on the t, it's going to give us clearly half of 1/3 is 1/6, and we got the delta t squared. There's a little digression up here when we talked about the average value of a function. I'll get to that in a minute. But that's what justifies this, and I want to remind you this result from very basic calculus. Okay, so the question now is, what's the kinetic energy of the wheel at time t? Well, kinetic energy is 1/2 mv squared. If, of course, that's for a point moving from moving through space. Okay, translational kinetic energy. But basically what you have is you have 3,000 kilograms all moving with this speed, and your mass, your kinetic energy is going to still be your 1/2 mv squared. So the kinetic energy is 1/2, let's say at time t, okay? If we assume that initial velocity is 0, so that v of t is 1/3 meter per second squared times t, and we're using t here instead of a delta t here, but the meaning is pretty much the same in this case. So you have this function, so your kinetic energy is 1/2 mass times velocity squared, 1/2 the 3,000 kilograms times the square of this velocity, which comes out 3,000 kilograms over 18. Of course, that could be reduced. You have a common factor of, 6. But we get this expression very clearly when we work this out. Generally then, the kinetic energy, generally kinetic energy is 1/2 the mass times the acceleration, which is net force divided by mass, times t, that quantity squared. So for any net force of this nature that remains tangent to the circle, and a mass distributed over the rim of that circle, a hoop, There's our general form of the kinetic energy as a function of time. Observe here that this is not all that useful, but if you needed the kinetic energy as a function of time, this is what you would do. You take your acceleration times your time to get your velocity, assuming we start from rest, as we did here. And you just simplify the expression. I should note that this F net squared T squared is the square of F net times T. T is presumably the time since you started up till whatever time it is now, and that's just the impulse, isn't it? So you might want to think a little bit about what that's telling you. Okay, the work done, which is F net delta S, where delta S is the distance a point has moved along the arc. Every point will have moved that far along the arc of the circle. And that should equal this expression at time t. And I kind of leave that for you to work out. You can figure out the delta S. Well, we did that here. So if we multiply that by the net force, what do we get? Do we get something that agrees with this? And it turns out that we do. Basically, 3,000 over 18 is the same as 1,000 over 6. 1,000 is a third of 3,000, right? 6 is a third of 18. Okay. Okay. So you can reconcile this as well. Now, this is in response to some problems that you've been asked to work on. These are ideas that you can use to contribute to your solution to those problems. Next thing we want to determine for this particular situation is what's the angular acceleration, what's the angular velocity, and what's the change in angular position. Now, these things have a very simple relationship to the quantities that we've already expressed, but we're going to work them out.